Science has been described as 1% inspiration and 99% perspiration.
3.38.
Sometimes the greatest challenges come from equipment and materials that are used in experiments. In most cases, the equipment has to be modified or even custom built for a special task. But behind it all is a person who's determined to persevere until the job is done. By the turn of the 20th century, J.J. Thomson had measured the charge-to-mass ratio of cathode ray particles, later known as electrons. He proved these particles had mass and a charge, but had only a rough idea of what the exact charge or mass might be. The search for the value of the charge on one electron became a major quest for physicists of the day. In this episode of A World in Motion, we'll examine the experiment that solved the puzzle, Robert A. Millikan's oil drop experiment. We'll collect and analyze data from equipment similar to devices Millikan used. You'll learn how balanced forces can be used to find the charge on a single electron, and you'll appreciate the challenge of doing groundbreaking work.
What's up, Angie?
We're building a model Millikan's oil drop experiment.
Why a model, Miranda?
Well, the real apparatus is expensive and tricky to use.
I see.
We figure if we see the principles in 3D, we'd get a better idea.
Hey, terrific. This will help you with the main ideas. It'll also give you a sense about what it takes to create a new piece of equipment.
I wouldn't really call this pile of stuff a new piece of equipment.
Well, wait till you add creativity and determination. Those are the key ingredients in every experiment.
Well, let's get started.
One of J.J. Thomson's assistants took up the search for the charge on an electron. He studied the behavior of charged water drops as they fell between two charged parallel plates. But evaporation of the drops was difficult to control. In 1906, Robert A. Millikan began his own versions of this experiment. At first, he tried to determine the rate of evaporation and then correct for it. After about 3 years of inaccurate results, Millikan hit on the idea of using oil drops to avoid the problem of evaporation.
So, these represent the plates, and the foam balls are the oil drops.
Looks good.
But what does it demonstrate?
Yeah, how did Millikan's experiment work?
Well, Millikan sprayed oil drops into the airspace between two parallel plates. What do you think happened?
The plates got coated with oil?
You expect the oil drops to respond to the force of gravity and fall to the bottom plate, right?
Okay. What if I told you that the spraying process gave the drops a negative charge, and there was a positive charge on the top plate and a negative charge on the bottom one?
In that case, the drops would be repelled by the like charges here and attracted by the opposite charges here.
You've got it. The drops experience an upward electric force. And when the potential is properly adjusted, the force of gravity could be balanced by the electric force. This means the electric force, QE, is equal in magnitude to the gravitational force, mg. We can find the electric field between the two plates using the potential across the plates divided by the plate separation. To solve for the charge on one drop, we rearrange the equation, which gives us the charge on one drop equal to the mass of the drop times the acceleration due to gravity times the separation of the plates, all divided by the potential across the two plates.
Let's try to get a sense of Millikan's overall strategy. Say a drop with a mass of 6.7 times 10 to the negative 16 kilograms is suspended between two plates. The plates are separated by 1.9 centimeters, and have a potential of 156 volts across them. How would you solve for the charge on this drop? Since the drop is suspended in the air between the plates, the solution to the problem begins with the idea that the force of gravity is balanced by the electric force. Once the equation is rearranged and the variables are substituted as they were before, we get the charge equal to the mass of the drop, 6.7 times 10 to the negative 16 kilograms, times acceleration due to gravity, 9.81 meters per second squared, times separation of the plates, 1.9 times 10 to the negative 2 meters, all divided by the potential across the plates of 156 volts. Remember, this is the charge on a whole oil drop, not the charge on a single electron. To find that value, Millikan had to look for a pattern in the charge on many oil drops.
So, these labels indicate how charge might vary among the oil drops?
Right. The values are in units of 10 to the negative 19 coulombs.
At first, we couldn't figure out how Millikan could go from charges on individual drops to the charge on one electron.
Yeah, but when we started to label the balls, we noticed the pattern in the values.
What pattern?
The smallest charge is 1.6 times 10 to the negative 19 coulombs. None of our oil drops had a smaller charge than that.
Yeah, and all the other drops have charges that are multiples of that.
Yeah, this one's twice that value, this one's 3 times that much, and this one's 4 times that much, and so on.
And your conclusion is?
We figure that charge comes in bundles of 1.6 times 10 to the negative 19 coulombs big.
We can have 1 bundle, 2, 3, or whatever, but you'll never get half or a third of that bundle of charge.
Way to go. Now, what name was eventually given to what you've called a bundle of charge?
Electrons.
Right. So how could you reinterpret your data?
This one picked up 1 electron, this one picked up 2 electrons, and this one got 3 electrons.
I think you've got it.
Millikan was awarded the Nobel Prize in Physics in 1923 for the oil drop experiment. His experiment showed conclusively that electricity was not a fluid, but instead was carried by particles. In the words of Angie and Miranda, the electron is the smallest bundle of charge. Physicists would likely say the electron is the quantum of charge. The word quantum refers to the smallest amount of something. So instead of saying that charge is lumpy, you could say that it's quantized. J.J. Thomson established that cathode rays were particles by determining their ratio of charge to mass. Millikan's result of the charge on one electron can be combined with Thomson's ratio. When the equation is rearranged, we see mass equal to charge divided by Thomson's value. Substituting precise modern values for both the charge on one electron, 1.602 times 10 to the negative 19 coulombs, and Thomson's Q over M ratio, 1.759 times 10 to the 11 coulombs per kilogram, gives an electron mass of 9.11 times 10 to the negative 31 kilograms. Electrons are particles with exceptionally small mass.
About how many electrons would you need to equal the mass of 1 grapefruit?
About the same number of grapefruits you'd need to equal the mass of the sun.
Well, that's a lot of juice.
J.J. Thomson experimented with cathodes made from a variety of materials. He found they all emitted particles with the same charge-to-mass ratio. So Thomson speculated that electrons were a building block common to all atoms. The mass value of the electron confirmed his notions. Millikan knew from chemical evidence that the mass of a hydrogen ion was 1.67 times 10 to the negative 27 kilograms. So if put in a ratio, the mass of the smallest ion, hydrogen, is still about 1,830 times greater than the mass of the electron. This calculation confirms Thomson's idea, since a building block or component must be smaller than the entire object.
Millikan's actual experiment took thousands of hours of data collecting and analysis, done over a period of years. The technology available to him gave Millikan his greatest challenges. It took very creative problem solving just to collect the data. For example, he couldn't use large drops. The force of gravity on them is too large to allow for a balancing electric force. So, Millikan had to use drops so tiny he needed a telescope to see them. That presented a whole new set of problems.
Millikan's main contribution to this experiment was the use of oil droplets, which evaporate more slowly than water, so the size of the droplets is maintained. In this modern version of the apparatus, the droplets fall through this little chamber and are viewed against that dark background. The bottom plate here is kept at ground potential, and the top plate, through this little contact there, is maintained at a high voltage. In this case, we use about 1100 volts. The droplets are illuminated on the side so that they appear as bright spots against the dark background. The source of ionizing radiation is kept over here on the side so that it can be introduced and used to deposit a charge onto the particles. So the droplets are then viewed through this telescope. We need a telescope because the droplets are so small that you need a fair amount of magnification. They're only several microns in diameter.
How do you measure the mass of a drop so small?
Well, to understand that, what you have to do is make use of the definition of the density of the particles. The density is given by their mass per unit volume. The volume is, of course, that of a sphere, so it's just given by 4/3 pi r cubed. So the mass can be written as the product of the volume times the density, which is 4/3 pi r cubed times the density.
So to find the mass, you need the radius of the drop. How can you find the radius of something so small?
To do that, you have to watch how the droplets fall. Millikan did this and figured out what the terminal velocity of the particles was.
When an object falls, it accelerates until it reaches its terminal velocity. This is the highest speed that a falling object can have. For a human being falling through air, the terminal velocity is between 128 and 200 kilometers per hour, depending on body shape. You can't fall faster than your terminal velocity because the upward force of air balances the downward force of gravity. When forces are balanced, there can be no acceleration.
In Millikan's experiment, an oil drop with a negative charge can be balanced between the two plates. Angie, what would happen if the plate potential were turned off?
If the plates weren't charged anymore, the drop would fall because of gravity.
And soon it would reach its terminal velocity.
Right. It reaches a point when the downward force due to gravity is balanced by the upward force on the drop. That upward force is called the viscous force.
So what affects the terminal velocity of the drop?
Well, let's take a look at the equation. It depends upon the square of the drop's radius and upon a list of other factors represented by the constant K,
Such as?
such as the difference in density between the oil and the air, the acceleration due to gravity, and the viscosity between the drops and the air.
I see.
The higher the viscosity, the greater the resistance to the motion of the ball. Viscosity indicates the relative amount of force that resists the flow of a fluid. Fluids that are thicker tend to have large values for viscosity.
When the viscous force is equal to the force of gravity, the oil drop reaches its terminal velocity. To find the radius of the drop, we divide both sides of the equation by the constant k. Then, take the square root. If you know the values of the terminal velocity and k, you can find the radius. So Millikan's method is now complete. Terminal velocity leads to radius, which then leads to the mass of a drop, and then to the charge on one drop. If I asked you to pull this all together, where would you start?
Well, how was Millikan able to find the radius using terminal velocity?
Why don't you use your model to tell me the parts you know, then I'll help you when you get stuck.
Okay, we've got an oil drop suspended between charged plates.
Then Millikan switches off the plates and lets the drop fall. Soon the viscous force of the air balances the gravitational force, and the drop reaches its terminal velocity.
Which is where I lose it.
Let's take it one step at a time. If a drop falls uniformly, how would you find its terminal velocity?
Speed equals distance over time?
Right. So long as you can get the distance and the time for a drop, you find the terminal velocity. So what comes next?
That's where the equation for radius comes in. Plug terminal velocity into that and get the radius of the drop.
Hold on. I still don't know what k is all about.
Try not to let that bother you. I've got the value for k. This is one equation that you can treat like a machine. Plug in velocity and out pops radius. If that still bothers you, then you can find out more by reading up on viscous force.
All right. What if I put in the values for v and k and get the radius? How would that get me to the mass of the drop?
Remember, the drops are spheres, and we know the density of the oil.
So with the radius, we can get the drop's volume and combine that with the density to get the mass of the drop.
Okay, now what?
Well, we said the drop was suspended. So if we knew things like the potential across the plates and their distance of separation,
Then we could finish it off the way we did the very first example.
I think another example would really help, one that shows everything.
good idea, Angie.
In this case, most of the drops are uncharged and fall under the influence of gravity. A few drops may have somehow acquired a negative electrical charge and move upwards under the influence of the electric force. Adjust the potential between the two plates so that the upward moving drop is stationary. We record the value of this potential and the plate separation. And we adjust the potential so the drop moves to the top of the space between the plates. The potential is turned off and the drop falls. We use the scale in the background to measure the vertical distance the drop falls, while we also record the time for this fall. Since the drop falls at a constant rate, we can find the terminal velocity by dividing the vertical distance of 0.0025 meters by the time of 38.4 seconds. This gives a terminal velocity of 6.51 times 10 to the negative 5 meters per second. Notice we keep an extra digit here since this is only an intermediate step.
One of the tricky things about the light foam balls is their sensitivity to air currents. But once again, the model reflects the actual experiment. A light pipe has to be used. Otherwise, the thermal energy from the light source can create convection currents that stir up the drops.
So we balance the drop and position it so it can fall between the plates. That way we can find the drop's terminal velocity, which allows us to calculate the radius equation for terminal velocity. This makes the radius of the drop equal to the square root of the terminal velocity, 6.51 times 10 to the negative 5 meters per second. divided by the constant k, 1.175 times 10 to the 8, with units of 1 over meters seconds. This leaves the radius of the drop equal to the square root of 5.54 times 10 to the negative 13 meters squared, which is 7.44 times 10 to the negative 7 meters.
The oil drop experiment is very temperamental.
Yeah, the drops are really small and are quite difficult to see.
3.56. I had a hard time making the proper adjustments for the measurements.
Now that we've calculated the radius of the drop, we can find the mass of the drop using the density of the oil. We rearrange the equation for density to give the mass of the drop equal to the density of the oil. 970 kilograms per meters cubed times 4 times pi times cube of the radius. 7.44 times 10 to the negative 7 meters, all divided by 3. This gives the mass of this drop as 1.68 times 10 to the negative 15 kilograms. Now we use the mass of the drop to find the charge on one drop using earlier data. When the charge was suspended, electric force on the drop balanced gravitational force on the drop. We rearrange as before and substitute in the data. That gives the charge equal to the mass of 1.68 times 10 to the negative 15 kilograms times acceleration of 9.81 meters per second squared times a plate separation of 0.0050 meters, all divided by the potential across the plates of 265 volts. So the charge on this drop is 3.1 times 10 to the negative 19 coulombs. This is very close to the value that would occur if the drop had picked up 2 extra electrons, 3.2 times 10 to the negative 19 coulombs.
That's a lot of work for one calculation.
We need to find the charge on one electron, so we need to use the same method for a bunch of drops.
And this thing's tricky to use, so each trial is going to have errors.
We need to have enough trials to average the results in a reliable way.
Millikan used to observe a single drop for almost an hour, and he had data for thousands of drops.
You earned that Nobel Prize.
We have a computer spreadsheet. We can collect the data, and the computer can do all the ugly number crunching.
Sounds like a plan.
Here it is.
Way to go. That must have taken a few hours.
Thanks. Now all we have to do is find the value of the charge on one electron.
Okay, Miranda. It's not as straightforward as the data from your model, is it?
We have some experimental errors that makes the pattern harder to spot, but the same approach should work.
Okay.
First, we have to figure out how many electrons we're dealing with.
Okay, so this one has 2. This one has 3. And 2 again at the bottom. And the rest all correspond to 1 electron.
Looks good.
So if we can find the total charge and the total number of electrons, we should be able to estimate the charge on just 1 electron.
The total on the left column is 22.50, and the total on the right is 14.
Great.
So, the average is the total charge divided by the total number of electrons.
Right.
So that's 22.50 times 10 to the negative 19 coulombs, all divided by 14 electrons.
Which gives us a value of 1.61 times 10 to the negative 19 coulombs for the charge on one electron. Pretty close.
All right. Persistence pays off once again. Well done.
Is this apparatus used today for real research?
Yes, it is. When Millikan first did these experiments, what he was interested in was learning more about the charge of the electron, and in fact looking at expanding our knowledge of the charge to mass ratio, which had been learned in earlier experiments. Today, what people are looking for are fractional charges. There's no reason that charges in nature have to be always built on multiples of the electron charge. It turns out, in fact, that we know that quarks have fractional charges. But quarks have never been seen by themselves. Quarks always come in groups. So a lot of people are trying to improve on this apparatus and do more and more sensitive experiments in an effort to try to find evidence of quarks that are by themselves.
The modern Millikan apparatus, used by Miranda and Angie, is a refined and simplified version of the original. It took great ingenuity for Millikan to create the equipment he needed, using what was available.
So, what did you learn about Millikan?
Well, for one thing, he was a man of many talents. Inventor, builder, mathematician, team leader.
And given the hours he and his graduate students spent on this, they must have enjoyed this work.
Well, scientists are driven by a passion to discover, and it's the satisfaction from this process that makes all efforts worthwhile.
Millikan had to compensate for primitive equipment by devising a painstaking method that required years of careful experimentation. His experiment really demonstrates the kind of patience and dedication that's often required in science. Thanks to Millikan's perseverance, the charge on one electron is known, a crucial piece of information for understanding this world in motion.